which is a nice change. Maybe. Oh, I don't know. I don't know if all you guys are. I'm trying to encourage everyone to not hold themselves too accountable for what work they're doing, but it's really easy to hold yourself really accountable for what work you're doing. Um, it's really easy and it's a really good idea, and everyone will enjoy it. So I talked about this a couple of times, tried to think about it on stream, but I didn't get very far. I'd like to get to the point where I'm actually doing new work with it. My camera seems slightly out of focus, but I want to rethink about how we talk about neural networks. So, if you've never come across a neural network before, don't be shocked if this did not put the cap on the pen. Just put it in my hand. Just dropped it on the floor. This is not a explainer of neural networks. If you would like that, I really recommend 3 Blue, 1 Brown. And then he has a series on neural network. Hey, Kira. Honestly, I'm still. So, step 1 of returning to an old idea is the long process of actually working out what on earth my progress was last time I was there. Like, the idea is half gone at this point, and I'm having to reinvent it. Because in some ways, this is a dangerous thing to say. I think the idea is already done. It's just now working through it a little bit. So the whole idea of this is networks built as multi-purpose black box. Then we like impose purpose on it. Through training it. So we go from I can do almost anything badly to I can do this thing well. And so what's actually going on here is we have some relatively unstructured network that could do any task. And basically everything is connected to everything. Very Hepworth. And it's just a complicated mess. I obviously haven't done everything connected to everything, but close enough. And these connections are just feeding things into some functions. But after a while, when we train it, although the connections never disappear, some of them become effectively very important and some of them become completely unimportant. A bit like if you, let's say you made a road network for a city, and rather than saying like this will be the main roads, you just laid down a bunch of roads and you saw where people drove, and the roads where people drove a lot, you expanded those roads. So you end up getting stuff like, this kind of has to feed to everything, but only a few of these connections actually turn out to be important. And the rest you just forget about. I'm going to add even more lines to this just to really make the point that, like, it starts out with every possible connection and then it goes down to just the connections you need. I just seen a comment. Oh, I don't know why chat is not up on the thing, so let me just fix that. I think that's browser source. Okay, that's not right. Too complicated. Okay, chat can only be seen from, for those in the know. Tell me about what you mean by you think synthetically rather than analytically. And when we say that these things are a black box, we mean that actually, even if you have this substantially simpler form, it's simpler, but it's still way too complex to interpret. This is a okay description of what we mean by a black box in computing. It's a system where actually the interpretation of what's going on in it is sort of impossible. Am I implementing chaos theory? Oh, every day we're implementing chaos theory. I will never stop talking about chaos theory. I'm actually kind of going in it the other way around because this training process, this process right here, let's zoom it out and discuss it in a bit more detail. This is the process of training. And this is a chaotic process because you start with effectively random weights. So the weights being the strength of these connections. And then you look for small changes which lead to improvements. You can only look for small changes because you can't jump that far in a single step. And then you just repeat, basically. So why is this a chaotic process? Well, imagine instead of a bunch of networks, we had, I think it's really, I love talking about things going on in computing spaces as basically well-intentioned dogs. So let's say we've got some landscape of peaks, and over in the background there's a huge peak. And this is our peak finding dog. So that's too small to read. I'm just going to draw them as a circle from now on. So the absolute simplest thing you could do, and this is how most neural networks are working, is you put him down somewhere, you just plop him at random, and he says, "Oh, I'm supposed to find peaks. I'll just go uphill." Um, which means that actually, whichever random place you plop him down, he'll end up in a different location. If you plop him anywhere in this region, all of this region goes to a single peak. And actually, this is the tallest peak. If his job is to find the absolute tallest peak, the issue is that this region is quite narrow. So you might plop him down here and he goes, "Whoop, yeah, up I go." But you have to be pretty lucky that you actually land in this region. So I think I'm trying to give a really basic overview of how these machine learning processes are working, not because that's the way I'm going to start with. I'm going to go this from a completely different direction. But I think it's always good to have in mind the context of the problem. Let's give our dog a name. Our dog is going to be called Grady. And second. So our dog, Mr. Gradient the Second, is just trying to find his way to an optimal place. This is a sort of, so if you tune on many of my streams, they vary wildly from relatively sane physics to relatively like stream of consciousness, something or other. One of the places where they overlap is that I'm fascinated by optimization algorithms of any kind, because I think actually you can see those optimization algorithms as having behavior that is very zoological. I think in a meaningful way we can do the cryptozoology of optimization algorithms. But let's start with Gradient the Second, who is just a peak finding dog. Goes looking for his peaks. Just going to read your comment, Kevin. What I mean is I start reasoning from within the system the minute I hear the first concept. Asking millions of questions in my head, changing variables in the system, trying to understand what will happen. An analytic person does not do that, but stands outside the system and tries to gather as much information and start solving things. Analytical is a lot more deductive. It gives you one answer. Sano mostly gets creative with that. So let's remake our landscape. Let's draw an actual 3D this time. And maybe we'll just put a couple of peaks down. I regret making this one taller. So let's say there's just two peaks here. Relatively low one and a relatively high one. Make that even taller. Let's just really make sure it's clear that this is the tall peak. we've only drawn two, but let's say there's kind of many off in different directions. We could ask, okay, what's the best way to find this peak? And one of the really good ways is to just stick down a few hundred of our dog thread. Because top down, this is looking kind of in 3D, but if we switch to a top down, I'm not sure, kind of contour map, we have one peak rapidly growing here and one peak that's substantially wider over here. What we're really doing is we're just plopping down. I need another colour. I have some other colours. Let's use them. If we just plop down how many have I put there? 8 gradient descent dogs. These ones will go straight into these peaks. These ones going to go straight up to these peaks. One like this is a bit uncertain. Maybe it'll kind of make its way around like this, or even make its way up here. There's actually quite a narrow balance that it has to work its way through. But in terms of what you were just saying about you just throw yourself in and ask millions of questions, think of those million questions as you're sticking in millions of peak finding dogs. And one like this that sort of just dawdles its way along, you're like, let's forget about that question. Let's put that question in brackets. One like this that goes straight somewhere important, you're like, yeah, this is an important dog. This dog is really telling me about the landscape. Because to ask a complex question, you're kind of just trying out functions you already have in your head and putting them together in a way that gets you some way towards what seems like an answer. So if I want to ask a complex question like, how shall I cook the tomatoes in the fridge? It's not very complex, and it's not high art, but there's a pretty much infinite number of answers to that, and they're all quite similar. So how do I actually choose one to do? Because I do actually have to choose one to do. I probably start just like what ifing. If I do 1,000 what ifs, some of them are stupid, like what if I just, I don't know, what's a ludicrous thing you might do with a tomato? Tomato, nice to cook with because you can't really ruin it. It's quite nice, whatever you do. Um, um, I don't know why I'm blank. Sometimes you just blank on stuff. Like a kind of crappy what if might be like, what if I just put it on some bread? Just tomatoes and bread. Um, and I could think through that whole thought process of like, would I enjoy it? How good would it be? But at best, just put the tomatoes on some bread is one of these meandering, not particularly useful peak finding ideas. If instead I'm like, wait, I got a little bit of balsamic vinegar, I've got a little bit of salt, chop them in half, put them in a pan, put on the vinegar, put on the salt, serve in a salad. Oh, I'm just racing my way up the peaks here. And not only have I solved the what should I do with the tomatoes in the fridge problem, but I also solved the um, what shall I do with spinach in the fridge, the what should I do with the balsamic vinegar on the shelf, and the what am I going to eat for lunch problem. Um, so this, you can tell that I did not prepare this example beforehand, so I did not learn a spell. This I would call decision making by unstructured search. You might notice that the title of the stream right now is Unstructured Learning. Um, I've kind of missed a step here. I do what times 1,000 and I follow the good ones. So this is a great way to do search, especially if the issue becomes, is 1,000 going to be enough? Like, I've here drawn a 2D space. And yeah, even the tomatoes problem I could turn into a 2D space. I could turn it into like what temperature do I make the tomatoes, and what level of salt do I make tomatoes. Unfortunately, cooking tomatoes actually, I've got to ask like, okay, so what, um, how much cumin am I going to use? And then actually also I need to ask the question of, um, like, how much oil? And also I've got the kind of similar but slightly different thing to, wait, instead of oil, do we use butter? And the temperature isn't just the final temperature, but also the rate of heating. It will depend on whether or not I eat the whole thing very quickly. And this space that I'm making a decision in becomes, just to pull these back out again. I drew a two-dimensional space and I'm like, yeah, I'm fine with this. But then quickly, I have a space that is, how many have I drawn there? 1, 2, 6-dimensional. And honestly, a question like this is probably happening in a space that is like thousands of dimensional. So it becomes the question of, how do I search space with a huge number of dimensions? And I need to do it efficiently because, I might get hungry for lunch pretty soon. Um, and that network I showed at the beginning, we can think of as a dimensional space. Let's start with a really simple network. Let's start with the XOR network. So this is arguably the absolute simplest network, kind of first thing taught in network classes, and also often the last thing that I would call network calculus taught. So this is a network where you feed in two numbers, I'm not going to use the perfect machine learning terminology here. We're going to feed in two numbers, and those numbers are either going to be 0 or 1. And I'm going to write down a thing which will tell me are they I forget what XOR actually tells me. Are they the same or not the same, I think. I should look this up. This is we'll find out as we work through it. And again, for anyone watching, just to remind that the intent of this is not for it to be easily understandable first time round. You're not doing a bad job if you're not understanding it first time round. It's just working through the logic, and I'm working through it at the same time. Okay, so XOR does. This is a nice way of making sense of it. We're going to put in A and B, two numbers. And the output. Don't know why I question mark that. That is definitely XOR. If both numbers are 0, we're only going to deal with zeros and ones. It's going to be a 0. If either one of the numbers are 1, it's going to be a 1. If they're both 1s, it's going to be a 0. So you could say that it's asking a question of like, are A and B different? And the answer's 1 if yes, 0 if no. So we could put in a 1 or a 0 to these, and we want it to output a number which tells us are they the same number. And I'm just going to draw out the network. I'm going to draw it in my language, which is I'll explain as we go through. So I want these lines are saying that these are both pluses. And these lines are saying that these are both minuses. And at each of these steps, I'm going to apply a function and I'll describe what my function looks like in a sec. My function is going to take in the two inputs, so I'm going to take in, this is the sum, all the inputs with some weight, and the weight is these numbers. And it's also going to take in some, what we call a bias. Okay. And the function I'm going to use for this example is a top hat, which if all these arguments add up to less than 0 is 0. If they add up to more than 0 is 1. So basically, this is a function which asks the question of its inputs. Are they more than 0 or not? If they are more than 0, it goes, yep, 1. Tick. They're more than 0. If they're less than 0, it goes, no, 0. So what happens when we pass two positive numbers into here? Well, if they're both 1, then we're passing 2 into this number, plus 0.5, so it's definitely positive. So if one of them is negative, then we've got 1 plus 0, which is still 0. um, oh, we want minus this. Then I think we want minus this, do we? Yes, we want minus. So this is asking, is this larger than this value, basically? If either of these are 1, then this is... I'm trying to avoid writing too much. This node is going to give you a 1 if A or B are negative. Oh, sorry, are positive. Or it's a 0 otherwise. So we could call this is anything positive. This one, it's going to give minus of this, plus 1.5. So it comes out to be asking, are both of these negative? Or are both of these 0? Sorry, I forget that we're dealing with 1 and 0. So if we know this is asking whether or not something is, whether either of these are 1, and this is asking if they're both 0. Well, if they're both 0, we don't care about this, we don't want it. So this can also be seen as the inverse of I both 1. A slightly better starting on this now, this isn't really my language for describing it, but I'm going to keep on walking through. Then we have 2 more positive gates, 2 more positive spans. And you know what? At this point, I'm going to leave this as an exercise for you at home. But one of the reasons that this is so often used is that actually a lovely thing that it's showing is that this is basically doing a check for or either both true, a check for not and, or and then a check for and of both of those. So we want to know, is either one of them 1? And are both of them not equal 0? So if at least one of them is 1, I think we want both of them not equal to 1. Yeah, that's what we're going for. So one of them is 1, but both of them aren't. Therefore, this condition is satisfied. Have I played Civ 6? Yes, I think about the Civ games kind of constantly. One thing that I'm trying to be quite fond about is that I think that for much more abstract reasons than because it's a game about motion, games are really good at teaching you the tools you need to start doing and thinking geometrically. So when we make neural networks, they don't look like this. They tend to look like, in this language, something like this. Just an insane number of nodes, with often they're all connected, so everything's connected to everything. So we have n nodes. In m layers, and between them they have w weights, w connections. So we can draw this all out like a network, but actually the values of each bias is just a number. Go for it. Thanks for dropping by. The values of each bias is just a number. So if this, and which direction to do it? Any number you can map to a number between 0 and 1 if you have a way of turning it into you just need a mapping between it. So let's say that we're going to write down all of these values as n numbers between 0 and 1 representing all the biases. And then weights, we have I don't love all of the old terminology like weights and biases, but so I might start dropping them as we go. So we could see the state of a network as a position. I'm not going to draw this very well because no one can draw this very well. It's kind of a mathematical fact that if you can draw a hypercube in a convincing way. Let's just add a few more directions. One more over here. This is not, and maybe I'll do a video sometime on drawing hypercubes. This is not a very good way of doing it. But we have, let's actually go back to just the plain cube, I think. In some ways I think that's easier to think about. We could express this, the state of this network, as just a position in an n plus w dimensional box. The only difficulty is that for the kind of network we might be using day on day to do something like suggest which YouTube videos you should watch, n plus w is very large. So it's my job to think about high dimensional spaces, and I can do a pretty good job. If you need to know the answer to a problem in 6 dimensions, give me a call. If you need to know the answer to a problem in 10 dimensions, send me an email. If you need to know the answer to a problem in 10,000 dimensions, starting to get a little bit iffy. But that's the problem we have here. We have that we're trying to find the best state of this network, the best structure of it, in this very high dimensional box. Let's pretend, for the sake of understanding this, let's move to the problem in a completely reasonable number of dimensions, like, let's say, 3. And to make the problem more understandable, easily understandable, we can use what I like to call the fish tank example. Somebody gives you a fish tank, a 3D box, truly three-dimensional, and they say, right, here's what I've done. I've put in this corner, I've put a heater that radiates heat out isotropically. And over on this wall, I've put another heater that radiates heat out still isotropically, but because it's a long, thin thing, it radiates it out in kind of cylindrical shells. And just to make it really complex, well, no, actually, that's enough for now. So they then ask you where is the hottest point. And how do we go about finding it? And even in this three-dimensional system, for nice, well-behaved sources of heat like this, there probably is an answer. But actually, if you then, if you then make it particularly complex, if you even, let's say, add a third heat source, it becomes harder and harder to find the hottest point analytically. So instead we have to work out, what's a pragmatic tactic for finding this hottest point? And one of them is do you remember our uphill dog? Well, we're going to get a bunch of uphill fish. We're going to drop in a 100 fish. If those fish if they're swimming in a direction that gets warmer, then they carry on. We're kind of designing our fish here, designing the fish that we can use to achieve our goal. Let's call them fish cyborgs. If they're swimming in a direction that gets cooler, they stop and choose a random direction. Wait long enough let some time pass, and they collect near to hotspots. You could see this as a selection of rules for useful fish. It's just a sort of cookbook of how we could turn a ton of fish into a device for finding the hottest part of this box. And so we can do this even if the box isn't 3D. Actually, I haven't used 3D anywhere here, apart from it's easy to think about fish swimming about in a 3D box. We could certainly do this if the box is 2D. So I think another great example of looking at this in 2D is you've got some lake, and you've got a little village by the side of the lake. Can't spell village. And you ask these villagers we're now swapping from the 3D example to 2D example. Where is the deepest part? The lake. And you could do exactly the same thing. You could send them out on 100 little boats, tootling around. And as they go, they are testing the depth. And if they're going in a direction where the depth is increasing, they keep going. And if they're going in a direction where it isn't, they just pick a random direction and go there. And you'd expect the same thing to happen. If there is one deepest point, maybe they all end up there. If there's a few deepest points, if the actual let's now, not to complicate it too much, let's draw some contour lines of the depth of the lake. So if it looks something like this, if the lake looks like this, they should all collect here. But if the lake actually has a sort of secret Marianas Trench in it that goes incredibly deep, then some fraction of them will collect in these two places. So it doesn't actually tell you exactly where the deepest point of the lake is, but it does give you a way of finding some pretty deep points in the lake. So what about in 4D? Well, actually, as we showed, switching to 2D doesn't matter. We can just do the same in 4D. They only need to move in along lines. Same all the way up. Eventually, we start to hit some problems. As we get to really large numbers of dimensions, we get the same tactic will work, but it's going to get really slow. If you think this is cool and would like to go and look into it more, it kind of all exists under, well, probably the umbrella terms of like optimization routines, or Monte Carlo methods. I don't know my terminology exactly. Optimization is a good thing to start with. And it's a lovely group of problems where we're having to look not for the absolute perfect classical math solution, but a pragmatic method for getting to a pretty good solution. So we know how to find the hottest point in the fish tank, give or take. Quick, I'm not going to try and draw it, but quick, extra credit assignment. What happens when one of those heat sources is the fact that the fish tank is near a window, and so it heats up and cools down at different points of the day, and another of those heat sources is attached to a plug on a timer, so it turns on only at night. And what you now actually find you're doing is this same problem, but in 4 dimensions, or one of those dimensions at a time, and actually the hottest point is going to move around the tank at different points of the day. But if you want to, there is a single hottest point in the tank, specified not just by a 3D position, but also what time of day it's happening. If you can then find ways to add more dimensions, keep on asking this question. There still remains an optimal position, but the paths you walk to it get more and more complex as we go up in dimensions. So if we go back to our very high dimensional network, is it worth trying to think about this as a very high dimensional space? I'm going to do a quick aside on how to think about dimensional spaces that really helped me. The position in a 3D box is just 3 numbers. It could be expressed as X, Y, and Z. Actually, it can be expressed by any 3 numbers that are linearly independent. But equally, we could look at a problem like, let's say, the evolution of a star, and we could look at it in age, mass, and metallicity, how much metals it's got in it, which is a proxy for how much of its fuel it's burnt. When we talk about things in X, Y, Z and Cartesian coordinates, those coordinates are describing an actual position often. But any 3 numbers which describe the state of a system can work the same. And indeed, things can evolve along paths. If you look at a star in these spaces, So we've got time, we've got mass. It's going to be hard to draw this effectively in 2D, but bear with me. And we've got metals. At the very beginning of time, the star has no mass, no metals. It then grows quickly through collapse. So it's going basically straight up this mass time thing. It then runs out of stuff to kind of eat up. So yeah, this is not working that well as a drawing because it's staying kind of in this plane. Like time ticks on, but it's not getting more massive very much. In fact, it might be losing a little bit. It's losing some to winds. But it also starts at its core burning hydrogen and helium into metals. So it starts going up in metallicity, going backwards into the box. Then what happens next to it could be one of a number of things. Like, let's say it could supernova, and so it would stay about the same in metallicity, but in a very short amount of time, a lot of its mass gets blown out. The evolution of a star is a progress through these three coordinates, and if we can describe that path and forces that guide it, we can understand not just one star, but every star. Equally, given that we've got this now slightly abstracted view of what a dimension is, we can't draw it anymore. Arguably we couldn't before. Sometimes we use W as the fourth. But we can still write down 4 numbers and say, okay, I guess those do point to somewhere in a box. Just like we might say about the star, that it has actually time, mass, metallicity, and maybe its spin matters. And often in physics, when we say that something can be represented by a few coordinates, what we really mean is that, like this example, not a bad one, if you wanted to represent this okay, the 2D view of just time and mass is pretty good. The 3D of time and mass and metallicity is better. But as we go up, like let's say we get to like 6 dimensions we're trying to represent it in. 6D we're going to add spin, we're going to add distance from the galactic center, and we're going to add we're going to add population of any planets around it. Let's say that aliens start to pop up on the planet and start using up the resources of the sun. We should probably be going to more and more accurate as we're in this way, because we just have more freedom to specify exactly where you are. But we also are going to more and more complex. One lovely result that comes straight out of dynamical systems is that any system which can be meaningfully represented in larger than 2 variables has the capacity to be chaotic. You can't have a chaotic system that is truly locked into 2-dimensional movement. It has to have a third somewhere. But our box for this very high dimensional network could be represented by a list of numbers, but that list of numbers might be huge. It might go through all the A's. I'll go drawing this back at this. That starts on the B's, and then it eventually gets to the Greek letters. And then actually we're running out of things, like symbols to talk about, so this is a bad drawing of it. This is a very bad drawing of it. I was trying to draw a flames emoji. Like, at this point we'd probably stop trying to represent it by symbols, but this number of dimensions might be so huge that you can still write down each one individually to express a position. Are you missing my drawing of the flames emoji? Um, but it becomes really hard to actually picture this vector anymore. And we've got to do something harder than picturing the vector. We're still looking for what's the best position. What are 10 great locations? Your doctor. Doesn't want you to know. Um, how on earth, when we train a network, does it end up in them? And the answer is basically that it does exactly what we did before. We just plop in a dot and we say, move through this space, going uphill, until you end up in a space where you're in a really high position. I should say, I think thinking of uphill is really helpful. You might ask, like, okay, what does uphill mean in a high dimensional space? And I think the step that I maybe have skipped a bit here is the uphill that made sense for a dog. Uphill translates to good algorithmic performance. So let's say our thing that we're writing, its job is to scan through BBC Good Food and find me some recipes for tomatoes that I want to make. You could ask, it could suggest something. It could then see, do I click on it? If yes, more like this. If not, try and suggest something else. And let's pretend, I know this isn't how search algorithms work, that it just gives me things one at a time. So you could ask, what's the percentage chance of a click? That is a great thing to optimize on. This uphill dog is just trying to make sure that the most fraction of the time I click, and it can change its behavior and check if I click more often, and it's just continuously trying to do its very simple job to get me to click on a recipe. So this is what's going on when you're training a neural network. There may be different ways to train it, but honestly there aren't really. Like most of the more complex methods are just that I know of. I work only near machine learning communities, certainly not directly in. But every network architecture I know of works somewhere along these lines. Like, how do I find some local optima? How do I find the position that I should be in this space? Um, I'm gonna go prepare lunch for me and my partner. I'm gonna come back and do some more afterwards because this has all been a bunch of prep talking for getting to what I actually want to play around with, which is a series of methods for working this out. From the completely other way up, not where is the best position for me in this very high dimensional space, but how is there an actually perfect position in a very low dimensional space. Talk about that later.